Good day, everyone. My name is Obembe Deborah Temitayo. I'm here to make a presentation of the summary of the paper, which is titled Application of Swarm Intelligence in Transportation System Optimization, which is authored by Dr. Olasumbo Agbola from the Department of Mathematics, Covenant University in Nigeria, Deborah Obembe, also from the Department of Mathematics, Covenant University in Nigeria, and Dr. Michael Agarna from the Department of Quality and Operations Management, University of Johannesburg, South Africa, and Artificial Intelligence Unit, Canadian College of Business, Science and Technology, Canada. This is my table of contents. Introduction. Swarm intelligence is an artificial intelligence technique that studies basic species teaming behaviors in various distributed systems. This basically looks at different species, both in animal and in insects, in the way they move, in the way they search for food, in the way they build their nests. And one of those systems include animal herding, ant colonies, bird flocking, bee colony harvesting, honey, etc. And one of the major swarm intelligence that we focused on in this paper is ant colony optimization. Ant colony optimization was developed by Marco Dorigo in 1992, and it was the first swarm intelligence-based algorithm. It focuses on the foraging of ants in their colony. What this means is that it looks at the way ants move from their nest to their food source in search of food, the way they behave when searching for food. Something unique about ants is that they do not have ears or nose, but they have eyes and antennas. And when moving from one place to another, they deposit a chemical called pheromone. And through that antenna, the ant is able to smell and taste the pheromone. And also, we'll be applying ant colony optimization to a transportation system. The transportation problem was developed by Hitchcock in 1941, and it focused on minimizing costs and maximizing deals and profits in transportation. But here in the paper, we're looking at how to minimize cost in transportation. The paper looked at applying ant colony optimization algorithm in finding the initial basic visible solution. And transportation problem can be solved through linear programming and also can be solved through finding the initial basic visible solution and also finding the optimal solution at the end of finding the initial basic visible solution. So we're using ant colony optimization algorithm in finding the initial basic visible solution and also comparing that solution to other traditional method of finding the initial basic visible solution in a transportation problem. So transportation problem, we have two types of transportation problem. We have the balanced and unbalanced transportation problem. Balanced transportation problem is when the supply is equal to the demand, also when the demand is equal to the supply. While unbalanced transportation problem is when the demand is not equal to the supply or the supply is not equal to the demand. So method of finding the initial basic visible solution. Like I mentioned, we have traditional method of finding the initial basic visible solution, which we're using AC ant colony optimization in comparing them. We have the least cost method, northwest corner method, and Vogel approximation method. Methodology, ant colony optimization. This equation number one is the probability of ants passing a chosen path with respect to time. Tau ij is the concentration of pheromone associated with that path. Then eta ij is the heuristic factor favoring that path. And how do you find the heuristic factor? That is 1 over Cij. And Cij is the cost of that path. Alpha and beta are parameters that controls the relative importance of the pheromone and the heuristic factor. Steps in applying ant colony optimization to transportation problem. First, we have to find the probability of each distance between the two locations by using the formula above. And the distance we are talking about is the cost. Step 2, we start allocation from the second highest probability. So because we are dealing with vehicles, ants have the tendency of moving on top of each other even when looking for food. But because we are dealing with cars, and that part is actually the shortest probability or the highest probability of people moving in that particular part. So we assume that there might be a congestion in the first part, in the highest part. So we start allocation from the second highest part till all the supplies and demands are met. Step 3, we test for degeneracy. Degeneracy is when the number of column plus the number of row minus 1 is also equal to the number of occupied cells. And if there's degeneracy, you stop at step 4. If there's no degeneracy, you can continue to find the optimal solution. So step 4, we find the total cost. Note in this paper, we said let our pheromone concentration be 0.5. That means we have assumed that evaporation has taken place and has taken half of the pheromone being deposited by the ant. And we say our alpha and beta is equal to 1. So these are problem statements. See the unbalanced transportation problem and the balanced transportation problem. For the unbalanced transportation problem, we have 5 columns and 4 rows. And if you sum up the supply, we have the sum of the supply to be 117, and for the demand, we have it to be 95. You can see that the supply is not equal to the demand. That means this transportation problem is unbalanced. Then for the balanced transportation problem, we have 4 columns and 3 rows. If you sum up the supply, we have 1,000, and if you sum up the demand, we have 1,000. You can see that the demand is equal to the supply, then it is balanced transportation problem. Ant colony optimization, this is the result for the unbalanced transportation problem. If you look at the unbalance now, we have an additional row, which is this additional column, which is D6, and it is called the dummy column. We add it, that means we want to fulfill the demand, like make the demand equals to the supply. So we are adding 22 to the demand, which now makes it 117, and the supply also 117. So we test for degeneracy. Degeneracy is equals to the number of column, which is 6, plus the number of row, which is 4 minus 1, that is equals to 9. So now, how do we know if there's no degeneracy? If we look at the allocations, we tend to fulfill both the demand and the supply. If we look at the column number 1, we have 25 and 5, which are the underlying number. And if we put them together, it is 30. If we look at the second column, we have 20, which satisfy the demand. If we look at column number 3, which is 15, which also satisfy the demand. Column number 4 is 10, which also satisfy the demand. Column number 5 is 20, and column number 6 is 22. If you now look at the rows, you can see that it also satisfies the supply. And how many underlying numbers do we have? How many allocated or occupied cells do we have? We have 9 on the table. So since n plus n minus 1 is equals to 9, and it's also equal to the number of occupied cells, then there is no degeneracy. Our total cost will have to multiply both the number being allocated to it, times the cost on the table, which gave us to be 389. So our result for the ant colony optimization for the balanced transportation problem, it goes the same way, but the only thing that is different is that we didn't add any dummy column or dummy row because the supply is also equal to the demand. So we test for degeneracy, number of column, which is 4, plus number of row, which is 3 minus 1, that is equal to 6. There's no degeneracy since the number of allocations also on the table is 6. So we'll find our total cost. In conclusion, this paper looked at swarm intelligence and also used ant colony optimization to find the initial basic visible solution in both a balanced and unbalanced transportation problem. It also compared ant colony optimization to the 3 traditional methods: least cost method, northwest corner method, and Vogel's approximation method, which was shown in the paper. This paper also showed that ant colony optimization can be used to find the initial basic visible solution, which was applied to the data given, and the total cost for unbalanced was 389, and for balance, we have it to be 3,650. In contrast, the least cost method gave us a total cost for unbalanced to be 472, for balance to be 2,450. For northwest corner, it gave us for unbalanced to be 547, and for balance to be 3,700. Therefore, Vogel approximation method, it gave us for unbalanced to be 374, and for balance to be 2,150. Ant colony optimization compares favorably with the least cost method and the northwest corner method. If we look at both the 3 traditional method and the ant colony optimization, you will see that the Vogel approximation gave us a least total cost, followed by the ant colony optimization, followed by the least cost method, then the northwest corner. If a transporter wants to choose a path to follow, or a supplier wants to allocate things or places, or a transportation system wants to allocate buses to travel on which route to move from one place to another, he would choose the Vogel approximation method because it gave us a least total cost. That means they will spend less money. And also, they might also choose the ant colony optimization, which is also favorable because it gave us a least total cost. Therefore, ant colony optimization can be used to determine the initial basic visible solution for a transportation problem. We recommend that this method be applied to real and large data, and we also recommend using the solution from the ant colony optimization to find the optimal solution. You can use both muddy or stepping stone method in finding the optimal solution. So these are my reference. Thank you very much.